Now, these videos, next few videos, are about what we call rearranging the integrand. So, taking our integrand here and being able to rearrange it. As we see it here, we can't integrate it, but in a nice way, because there's manipulation that needs to be done. So, for example, the first one here is where we've got the degree of the numerator and the denominator are the same. Now, we saw a few things like that with our partial fractions. So that's part of the problems that will come up with partial fractions. But this is also something that needs to be addressed, because what we need to do is do one of a few things. You can do polynomial division to do this. I prefer to try and rearrange and decompose 6x here. Now, because I know 3x plus 2x is going to go into that once, or twice in this case, because 3x will go into 6x with a remainder. I know I can get my numerator to be two lots of 3x plus 2. So if I do that, now the problem is if I go with two lots of 3x plus 2, that gives me my 6x, but also gives me a plus 4, which isn't there. So if I'm going to add 4 to this one, I'm going to have to always subtract 4 as well. Now you can see, hopefully you can see the advantage of doing that, because that's going to cancel down. The 2 lots of 3x plus 2 on 3x plus 2 will cancel, just leaves me 2. And I'm left over with my remainder of minus 4 on 3x plus 2. Now if you did polynomial division of those two, this is what you'd come down to. You'd go in twice with a remainder of minus 4. And that would give me a fraction of 4 over 3x plus 2. But when I do that, that now becomes a situation where I can integrate that one just using our 2 unit, because that's that's close to the derivative of the function over the function. I really need the 4 out and need a 3 there, so 4 times the 4 on 3 times 4 times 3, sorry, would give me the 4 on 3 out the front, and the 3 over the 3x plus 2 integrates to give me a log function. So there's manipulation that can be done once I'm there, but I need to get just because it's a linear function, I need just a constant on top to be able to go back to a log function. So that's what a lot of these ones will do. This one's a little bit harder because it's 1 minus x into the x to the power of 4, which would be a little bit difficult to play with. But again, keep in mind that you could do a substitution. So if we let u be equal to 1 minus x, which means our denominator starts to become nice and easy, x can be written as 1 minus u. So I get a minus du there, so the minus can go out the front for the du. But then 1 minus x to the u to the power of 4 can be expanded that way. Now I've just used the binomial theorem to expand that. We know the binomial theorem, so that can come into play very nicely there. But then I can start to simplify this, because that has now got a common denominator that's very nice. 1 on the u cancels with the 4u, with the 6u squared, 4u cubed, and the u to the power of 4, gives us an expression that's very easily manipulated to do our integration. And now there's our expression once it's integrated and the substitution put back in. Now again, you could probably try and do your polynomial division. That's going to be a little bit ugly. It's going to be a little bit ugly, because you'll end up with things like this. Like you'll end up with something not very nice. You'll end up with all these terms because 8 minus x goes in, and so you'll be able to get down there, but not very nicely. So the substitution is a nice way to go. Here's one's a little bit simpler. X squared on x plus 1. Well, I know that I can start to manipulate x squared there, because I could write it as x squared minus 1 plus 1. Well, that's going to be the same as there, but that comes down to x plus 1, x minus 1, which can cancel with the x plus 1. So that just gives me x minus 1 plus 1 over x plus 1. Again, x plus 1 goes into x squared, x times, and then we get a minus 1 when we do goes into the next term, and we have a plus 1 as our remainder. But again, you can see how we come down to something nice that we can then integrate. Either it's just straight polynomial integration that we've done before, or something that integrates to a log function. This time, 2x minus 3 requires us to do a little bit of manipulation, because we can write that as minus 1 minus 2, and the minus of minus 2x make it a positive. So you can see how I've manipulated to get the same as 1 minus 2x, because minus 2x goes into 2x minus 1 times, and then we're going to have a remainder. And that's decomposing it there. That just allows me to do a little bit easier than polynomial division, I think. So we get the minus 1 minus 2 over 1 minus 2x, which is going to integrate to a log function. And minus 1 just integrates to minus x. So 3x minus 1 going to x squared. This one's a little bit harder. If we look at the polynomial division of this one, so I haven't done the full polynomial division, but if I do that, I get the 1 on 1/3 of x plus 1/9 plus 1/9. Sometimes you have to do polynomial division. It's just a little bit too hard to try and manipulate. So basically, by our polynomial, when we do the polynomial our division transformation, x squared could be written as 3x minus 1 times 1 on 3, 1/3 of x. So it should be 1/3 of x there, so not there, plus 1/9, and then plus 1/9 as well there. So there's our polynomial transform, the division transformation with that one, which when we expand the bracket, we get 1/3 of x, 1 plus 1/9 plus the 1/9 on 3x minus 1 when they do the cancellation there. And so we can integrate, start to clean that up and factorize 1/9 at the front. Don't have to, you can integrate there, integrate. But we get 3x to integrate, which gives us 3 on 2x squared. Integrate 1 gives us x. And derivative of the function, we need a 3 on there, so it'd be a 1/3 out the front. So it's where the 1/3 natural log of 3x minus 1. And again, we put that, you'll see that a lot in the extension 2 course, where you can put the absolute value around it. So it's really because we can only take a positive value there of that. And then plus, don't forget our constant integration. So let's have few manipulations, doing division of polynomials, or just decomposition using our division transformation as well, and some substitution to try and simplify the problems that we're going to face, that we need to look at when we've got a polynomial where, or an expression where the numerator is greater than the denominator.